Now we will discuss some solved examples on the application of magnetic field. So, in the first question, it is given like you can check up the figure as shown in the diagram, two mutually perpendicular wires. So, the wires are shown here. As shown in the diagram, two mutually perpendicular wires are placed very close to each other but are not touching each other. The regions where the intensity of magnetic field is 0 is, or if more than two options are there, or more than one option is there, that you have to select. First option is A only. The second option is B and D. The third option is A and B. The fourth option is B only. I hope you have understood the question. The figure is given to you and wires are mutually perpendicular, very close to each other. However, they are not touching. We have to check up the regions where the intensity of magnetic field is 0. Four options are given. Now check up the solution and see the diagram. So according to this, we find that region B, field due to I1 is into the page and field due to I2 is out of the page, shown by the arrows. So at some point we expect these fields to cancel and add up to give 0. Similarly, in region D, check up the figure, field due to I1 is out of the page while field due to I2 is into the page. Therefore, again, somewhere fields A and C, fields due to I1 and I2 are in the same direction and cannot give 0 on addition. Thus, the correct answer is 2, that is B and D. Now, we come to the second example. A straight horizontal stretch of copper wire carries current I, that is equal to 30 amperes. The linear mass density of the wire is 40 grams per meter cube. What is the magnitude of the magnetic field needed to float the wire, that is to balance its weight? Now, four options are given: 147 G, 441 G, G stands for Gauss, 14.7 G, 0 G. Our aim is to find, that is, field needed to float the wire, that is to balance its weight. Weight is mg. Now, for length L of wire to balance, the force due to magnetic field, that is mg, and weight also equal to BIL or ILB, that is equal to mg. Equate the two numbers. F is equal to ILB. Therefore, B is equal to mg over IL, and that is equal to m over L into G over L. So, by calculating it, the correct answer comes to the first option, that is 147 Gauss. Now, in the third example, you are given a closed circuit with radii A and B carrying current I. The magnetic dipole moment of the circuit is. So, our aim is to find the magnetic dipole moment. The magnetic dipole moment is given by function current into area. Current is taken as I, and according to the figure, area can be taken as half pi a square plus half pi b square. Making the calculations, and the net result will become half I into pi into a square plus b square. Now, in the next example, a current I is flowing in a square coil of side A. Find the value of magnetic field at the center. Now, see the diagram. PQRS is current carrying square of side A. So, A is the length of the side, due to which magnetic field at its center O is given by function B is equal to 4 multiplied magnetic field due to PQ. So 4 into B and PQ. The meaning of the symbol BPQ means magnetic field due to PQ. And by putting up the values, 4 multiplied by and the value of magnetic field due to PQ, that is given by function mu naught I over 4 pi r into sine theta 1 plus sine theta 2. Here theta 1 equals to theta 2 equals to 45 degrees as shown in figure, and r is a by 2. So if we calculate the value of B, it comes to be 2 root 2 mu naught I over pi a. After substituting the values, we'll get the value of B. Now in example number 5, in the body shown in the diagram, I current is flowing, radius of circular part is r and the linear parts are very long. Find magnitude of magnetic field at O. Now look at the figure again. The figure is shown. The direction of arrows are indicating the flow of current. B stands for magnetic field and B naught is magnetic field at O. So our question is, in the body shown in the diagram, I current is flowing, radius of circular part is r and the linear parts are very long. Find magnitude of magnetic field at O. B naught is equal to magnetic field due to AB plus magnetic field due to BCD plus magnetic field due to DE. Put up the values, simplify the result, which comes to be mu naught I over 4 pi r into 3 over 2 pi plus I. Now in example number 6, two wires ABC and DEF are arranged as shown in the figure. Current I is flowing through them. Value of magnetic field at O will be. Now see the figure again. In the figure, we are finding the arrows are indicating the direction of current. Distance from B to O or O to E are taken as A, and we are finding there is a wire FE and the wire is BC. Two wires ABC and DEF are arranged as shown in the figure. Current I is flowing through them. Value of magnetic field at point O will be. Now magnetic field at point O will be magnetic field with respect to AB plus with respect to BC plus with respect to DE plus with respect to EF. If we compute the values, the net result will become mu naught I over 2 pi A. Now, we come to example number 7. In given figure, find the magnetic field at the center O. Again, look at the figure. BCD carrying current, direction of current is from B to D via C. A is a point at infinity, AE is also a point at infinity. However, the current flowing in this straight system is I. And angles at O are shown as 45 degrees each, like OB and OD. The radius is R. B naught is equal to, that is magnetic field at O. That is magnetic field with respect to AB, with respect to BCD, with respect to DE. Put up all the values, add them algebraically, and the result is found to be root 2 plus pi by 4 into mu naught by 4 pi 2I divided by R. Now, a current 2 amperes is made to flow through a coil which has only one turn. The magnetic field produced at the center is 4 pi 10 to the power minus 6 Weber per meter square. You will remember that Weber per meter square is equivalent to 1 Tesla. Then radius of the coil will be how much? Now check up the solution. Magnetic field at O is given by function mu naught Ni over 2R. R is radius. And number of turn, that is 1. So computing the values, B naught is found to be mu naught I over 2R, or R is equal to mu naught I over 2B naught. Compute the values, get the value of R, which is found to be 0.1 meter.